Hello everyone, this is Behzad, and this talk is about two-round concurrent 2PC from sub-exponential LW, joint work with Sakrishna, Rex, Julio, Ahmad Reza, and Amit. We start with the problem statement of the concurrent 2PC and the definition of the 2PC computations. 2PC computations, in short, is a protocol between two parties, let's say here Alice and Bob, which jointly wants to compute a function f over their secret, which each one is given x and y as a secret input. And the security that here we are looking for is that the adversary should not learn any information beside the output z, and usually it can be proved by simulation-based security. And by concurrent security here, we mean that the protocol remains secure even the adversary sees many instances of the protocol are executed in the parallel. And in this talk, we will answer, in this talk and in this word, we will answer to this question that can be achieved to run concurrently secure two-party computations under simple post-quantum assumptions in the plane model. Before going to the construction, let's just have an overview of some terminology that we will need this to get the construction. So we start with the concurrent setting. This is actually a more realistic setting, which allows parties to participate concurrently in arbitrary many instances. But there is an impossibility result in this area. It's by BPS in 2006, saying that the standard definition of concurrent security is impossible in any round in the plane model, it means without any trust set. But later, to overcome to this impossibility results, there has been some efforts like the bounded concurrent model by PASS 2004, and also using the multiple ideal query model by Goyal and Jain in 2013, and also input indistinguishable computations by Micali and PASS in 2006. And also a relaxation version of the simulation security, which is called superpolynomial simulation, or in short SPS, by PASS in 2003, which in this work we will focus on this. We will use in the SPS paradigm to prove our 2PC computation, our two-party computation. And about the round complexity, so here where we are, our protocol is in the simultaneous exchange message model, and at the end each party will get the output, which is called two-side outputs. In such a model, in every round, each party sends the first message simultaneously, and in the second round they will continue to sending the second message again simultaneously. In this area, there has been also some efforts to get the round complexity better and better. In 2014 and 12, there was a construction which actually was constant round protocols, approximately 20 rounds, and also JKP in 2017, it decreased in 5 rounds with SPS security. And in 2017, against BGJKS, they construct the concurrent MPC in 4 rounds with SPS security. And quite recently, ABGKM in 2021, they constructed a 2-round, which is supposed to be a round optimal MPC, but standalone, not in concurrent security, in the plane model, assuming sub-exponential NIV and sub-exponential SXDH, and the existence of the non-interactive, non-malleable commitment. And quite recently, FJK22, they constructed concurrent 2-round MPC protocol, but under assumption sub-exponential quantum hardness LWE, and sub-exponential classical hardness SXDH, and the existence of sub-exponentially secure I/O and time-lock puzzles. So in all of these works, either using some many rounds, more than 2 rounds, or is in the standalone security, not in concurrent setting, or based on some classical assumptions like SXDH. So now our goal is to construct the concurrent 2PC based on some post-quantum assumptions, and in 2 rounds. But before that, let's just have a quick overview on the standard simulation real and ideal paradigm that later we will go through to the SPS simulation paradigm. So in a standard simulation proof, normally there is 2 worlds, real world and ideal world, which in the real world, let's say Alice is interactive with some malicious bug or adversary, and in an ideal world, there is a functionality and a simulator which jointly they want to simulate the protocol in a way that at the end the output of real and the ideal world should be computationally indistinguishable. In this model, simulator usually runs in polytimes, and so the adversary also is polytimes. But in SPS simulation paradigms, simulator runs in the super polytime. And why this is meaningful? Because then then F is secure against super poly adversary, which we are going to use this SPS simulation paradigm to prove our constructions. Now let's see how is our results. Our main results is constructing 2-round concurrent secure 2-party computations, which is based on single and standard assumptions like sub-exponential hardness LWE, which is supposed to be post-quantum secure. Means that our protocol, our 2PC, doesn't need the existence of 1-round non-malleable commitment. Instead, this is going to be based on 2-round non-malleable commitment, which is known by Corona and Saha in 2017 based on sub-exponential LWE. And also our construction will not be based on the existence of non-interactive witness indistinguishable arguments or time puzzles. And also as applications of our construction, we show that how one can construct the first 2-round page passport authentication key exchange scheme in the plane model, which means resolving a long-standing open problem in this area. And also the first concurrent 2PC for quantum functionality in the plane model when the output and input are classic. But in this talk, we mainly focus on the main results and show step by step how we can construct this 2-round concurrent secure 2-party based on LWE assumptions, based on sub-exponential LWE assumptions. We first start with the observation from ABGKM 21 for the 2-party computations in the simultaneous exchange messages. So in such model, we assume that each party first sends the first message in the first round simultaneously, and then continue it in the second round, again sending the second message simultaneously. So in that case, let's say Alice first sends the first message of the protocol, and Bob is malicious, and here the adversary, adversary is rushing adversary, so he might wait and gets the message of Alice, and then after seeing the message, compute his own message and sends the first message of the protocol and go on. And then means that the adversary here can actually somehow malform the round one of the message of the 2PC in a way that at the end, besides getting the output as Z, which is f of x and y, it will get some extra information of Alice's input x, which is going to be secret. To prevent such things, one should actually allow Alice to validate the first round of the message from Bob. So in that case, Alice first validate the first message of Bob, and if it's well formed, then she will answer to she will follow the protocol in the second round. One naive idea actually here is to use some proof, let's say correctness proof, like a zero knowledge proof, in the first message, in a way that each party can attach a zero knowledge proof in a way that to show the well forms of the first message. Then each party can just check the proof, and if the first message is well formed, then they will continue to the second round of the protocol. But what is the problem here is that non-interactive zero knowledge needs some extra assumptions, like, for example, being in some trusted setup or common reference string or in short CRS, which is not in the interest of this paper, because the goal is to get it in the plain model. Now, the observation actually showed that if one can allow Alice to somehow lock the second message of the protocol in a way that if Bob is honest, then he can unlock the message and compute the second round of the protocol. And if Bob is malicious, then he shouldn't be able to unlock the Alice message. So now we show that how we can actually instance this observation to get our concurrent two-party computations in 2 rounds. Our protocol mainly rely on the following 4 primitives: a 2-round non-malleable commitment, a 2-round SSP-OT, a 2-round strong SPS zero knowledge, and garbled circuits. So in a way that each party PI, which PI could be either Alice or Bob, refers each one just commit to its input by using the first message of the non-malleable commitment and the first message of OT, which the first message of OT later will be used by the party I, by each party, in reconstructing its own output. And also, the first message of the non-malleable code will help the other party to construct its own output. And the non-malleable code actually here is to prevent the honest party from learning null outputs. And the next question would be how we can do to prevent the adversary from learning the output. Here actually comes from the SSP-OT primitives, which allows an adversary that only unlock the protocol output if it knows the input of the first message of OT in the first round of the protocol. So with this thing, seems that we already come up with the problems that we explained, that we saw in the previous slides, and the observation that we have. But the question is, are we done now? Not yet, because there might be an attack here. For example, let's say Alice is malicious, and in that case, Alice use different inputs for non-malleable commitment, first message of non-malleable commitment, and first message of OT. So, and it turns out that at the end, Alice can compute f of x and y, but Bob will compute f of some x prime and y. Which means that to prevent such an attack, still we need to somehow make a link between the non-malleable, the first message of the non-malleable commitment and the first message of OT. So to this aim, we actually use another we force each party to actually, besides committing to its input by using the non-malleable commitment and the OT, the first message of OT, they should also commit to the randomness used for the non-malleable codes, non-malleable commitments. And then in the second round, besides sending the second message of non-malleable commitment and the second message of OT, each party also computes the garbled circuit C on the input and also giving a SPS ZK, which this SPS ZK guarantees that the same input is used in the non-malleable code and in the OT and in the garbled circuit, which actually this SPS guarantees the well-formness of the three primitives that use the same input, let's say X or Y, for Alice and Bob, respectively. And also, this commit to the randomness that used for the non-malleable code in the first non-malleable commitment in the first message later enables the other party to construct its garbled circuit to only reveal the output if this randomness is correct. So by this modification and by using that case, we can see that we can get we can actually satisfy the conditions that we saw in the observation in the previous slides. And since all of the primitives are all of the four primitives down based on LW sub-exponential LWE, and also can be constructed either in first or two rounds. So at the end, our protocol also will be in two rounds and based on sub-exponential LWE, which is supposed to be post-quant. Thank you, and I will refer for more details to the full paper, which is actually in the ePrint.